A spring attached to the ceiling is pulled 7 centimeters down from equilibrium and released. So let's draw a line up here, and we'll draw another line here. And this will mimic the spring. And so we will pull it down. If this is 0 centimeters right here, we will pull it down to 7 centimeters right here. And so the spring is going to start right here, and then it's going to oscillate back up, and it's going to oscillate, or it's going to come back down, but it's not going to quite reach this point. It's going to be 11% less than that, and it's going to do it again and again and again, and keep losing until it eventually turns into until it's back to normal again. This is an example of damped harmonics. So what we need is a function that can help us model damped harmonics. So let me see if I can just find that quickly for you here on OpenStax. Damped harmonic motion can be written in the following way. F of x is equal to a times e minus c t. And I need to decide if I'm sine or cosine. I started at the very bottom, so that's going to be cosine. But here's the thing. Am I positive or am I negative? And the answer to that question is, this is my max. I know it's weird, but my ceiling is up here. I'm starting from max up here. It's upside down. Everything's upside down. But 7 meters is my max. So, or centimeters is my max. So this is my function. And I have some information that I can put in. For example, my amplitude is 7 ECT. And my W is going to be related to my frequency. Remember, my frequency is equal to, I believe it is 2 pi over W. Or is it W over 2 pi? It is W over 2 pi. It's the complete opposite. It is W over 2 pi. The period is 2 pi over W. So my frequency has actually been told to me it's equal to 20, which means that W is equal to 4 pi, or 40 pi. So this cosine 40 pi t. All I need is this. And I have that information. The amplitude decreases by 11% each second. Well, interestingly enough, there's a couple of things that we need to understand. Number one, this is a Euler function, and it can be easily written if I knew a dampening factor. But I'm not told a dampening factor. I'm just told that the amplitude decreases by 11% each second. That's not a dampening factor. That's just the amplitude decreasing. So if I don't have a dampening factor, I can get one. Or I can understand the following. When the spring is released at 7 centimeters, after 1 second, the amplitude is going to decrease by 11%. After 2 seconds, the amplitude is going to decrease again by 11%, and so on. This is just simply 7 times 0.89 raised to the t. So I can write that. Times cosine 40 pi to the t. And you're asking yourself, well, what happened to the Euler function? What happened to the Euler value, e to the negative c times t? This value and this value, if I were to find the dampening factor, will give me the same value. If I knew c, then I can write it as 7 times e raised to the dampening factor times t. But I don't know c. Could I get c? Sure. All I do is I convert 0.89 raised to the t to a Euler function and solve for c, probably using a natural logarithmic function. I don't need to do that. I've already written a function in terms of t, of course this should be f of t, not f of x, that gives me any information that I need based on the number of seconds. For example, what would my amplitude be after 10 seconds? I would be able to get that information here. What would my spring be doing after 10 seconds? What would the amplitude be? I would be able to get that information from here. So there that is.